Dmitry Shabanov, who will speak about a very long name. Okay, let's start.
Okay, thank you very much. So here's my outline of the talk. So first of all, we will understand what is the statement of the problem, then discuss known results, then I will present some new result and discuss the method that was used to obtain this result, and finally some generalizations will be given. Okay, so let us start. So we consider random hypergraphs, but it is always good to start with random graphs because it is more classical model. So let G of NP denote the binomial model over random graphs, which means that we have n vertices and P is some parameter in which, with probability P, every two vertices are joined by an H independently from each other. So, and the general problem is the following. So, given a function, we want to find the asymptotic behavior of the chromatic number over random graph. This is higher than G over P. Since the chromatic number over random graph is a random variable, so the proper formulation will be, so we want to find some limit distribution, if it exists, for the chromatic number. Okay, what is known? So first we consider the dense case when P is not a very small function of n. In fact, NP tends to infinity. If P is a constant, then there is a celebrated result of Professor Balabash, which states that the chromatic number is asymptotically n over 2 log n. This is 1 minus e to the power minus 1. In probability, it means that we have the log of the large numbers for the chromatic number. But of course, this proof works not only for constant probability. If P is a function tending to 0 but not very fast, then it's also true. And the remaining values for the dense case were covered by the theorem of Tomasz Luczak. He proved that if P tends to 0, but NP is not small, it's greater than some constant, then we have this asymptotic representation, so which means that even P tends to infinity, then this is 1, and we have this law of large numbers, NP over 2 log NP, so the chromatic number is obtained. And but you see that if NP is a constant, then we don't have the asymptotics for the chromatic number, because here we will have only some bounds. So the chromatic number is less than one constant and is greater than some other. So we are interested in the following main regime. This is the main regime of the Stork. So this is a sparse case. Sparse means that P is just a constant over n. If P is an infinitesimal function such that NP tends to 0, then it is not interesting, because in this case our graph will be too colorable with high probability, so the chromatic number will be 2 or maybe 1 if it is empty graph. Okay, so the sparse case, constant over n, we have some positive constants. For this regime, Luczak proved that there should be a 2-point concentration for the chromatic number, which means that, in fact, it is true not only for the sparse case. For P, at most n to the power minus 6 over 7, there is some function h of n such that the probability that the chromatic number lies between h and h plus 1, so 2 values which are adjacent to each other, this probability tends to 1. So with high probability we have a 2-point concentration. In fact, for in the sparse case, there should be a one-point concentration for almost all values of the parameter C, because it is known that the property of r-colorability has a sharp threshold postulated by Loftus and Friedman, which means that, but we know that the chromatic number is bounded in the sparse case. So there should be one point for almost all values of C, except some special points in which we don't know what will happen. And the question, okay, but this is the existence. What, given a constant C, what is the value of this function h of n? And this was established by Loftus and Nauer in 2005, and they proved the following. So if we have sparse case, so given C, let RC denote the smallest r such that C is less than 2r log r. So if we have a constant C, we can calculate this number RC. Then the chromatic number of our sparse random graph is between RC and RC plus 1. So we know this function h of n for every C. But in fact, as I told before, so there should be one point concentration. So we should choose RC over RC plus 1 for almost all values of C. And it is not very difficult, and maybe it is easy to prove that if C is larger than 2r log r minus log r, then with high probability our random graph will not be r-colorable. So the chromatic number is at least r plus 1. And this gives us the following picture. So we know if C is less than 2r log r, then with high probability the chromatic number is at most r plus 1. So this follows from the result of Loftus and Nauer. Okay, if C is between 2r log r and minus log r and 2r log r, then with high probability the chromatic number will be exactly r plus 1, because we know that it cannot be r. So its high probability is greater. So in this interval we have a one-point concentration. We have the limit distribution for the chromatic number. Okay. The next point from the theorem of Loftus and Nauer is 2r minus 1 log r minus 1. So between it and this previous 2r log r minus log r, we have a two-point concentration, r or r plus 1. And it isn't, but with what probability we will have r, and with what probability we will have r plus 1? It is unclear. So we have some interval in which, so between this number and this number, we know the limit distribution roughly for half values of the parameter, because this value is somehow between. So the difference between this and 2r log r is log r, and between this and this we also have asymptotically log r for the chromatic number. And the question is whether we can reduce the length of this interval to a bounded value, bounded for all possible values of r. And it was done by Kocaglan with Velenchik and Kocaglan himself. So they proved the following. So if C is less than 2r log r minus 2 log 2, so just a constant, 2 log 2 plus something tending to 0 with growth of r, then with high probability our random graph is r-colorable. Surprisingly, he was able to improve also the upper bound. So if constant is greater than 2r log r minus 1, then with high probability our random graph is not r-colorable. So we have here obtained with Velenchik together. So they obtained the interval with a bounded length, in which we don't know the limit distribution of the chromatic number. We know that it is r or r plus 1, but with what probability have r or r plus 1, it is unclear. So the unmuted interval now has a boundary value 2 log 2 minus 1, so roughly this 0.338. So this is for graphs. And now we consider random hypergraphs, so this is the main topic of the talk. So let h of nkp denote the random model over random k uniform hypergraph, so we have them vertices, and every k subset is included as an h with probability p independently from each other. And we're interested also in the same way, so we want to find the chromatic number over random hypergraph to obtain some limit distribution. So the chromatic number of a hypergraph, let me close that, just the minimum number of colors required for a proper coloring. Proper means that there is no monochromatic edges. In the dense case, when P is much greater than, sorry, this should be minus, and to the power minus 1 over k minus 1, the symptotic behavior of the chromatic number was obtained by Shamir in the very dense case and by Kovacevic Sudakov for p close to this value. And we deal with the sparse regime again when the number of edges is linear, is a linear function of the number of vertices. So p is equal to cn over n choose k. We consider that c is fixed, k is also fixed, and n is a large parameter which tends to infinity. So this parameterization is not the same as it was for graphs, because, so roughly for k equals 2, we will have p equals 2 constants, 2cn or 2c over n. So 2c over n asymptotically. So all the results which will be stated for hypergraphs, graphs, they hold with constant, you should, twice, this is a constant. Okay, if you have some hypergraph result, so you can obtain this. It's true for graphs, but with constant, with twice larger. So, the analog of the theorem of r-colorability for hypergraphs was proved by Dyer, Fries, and Greenhill recently, but maybe not very recent, but it's again repeated in 2015. So suppose P, we have this regime, sparse. Fc is greater than this value, so r to the power r k minus 1 log r minus 1/2 log r. Then our random hypergraph is not colorable with high probability. This is just an application of the first moment method. Okay, and they prove the following. So there exists some number between this r to the power k minus 1 log r and the previous point. So with r one smaller, so r minus 1 to the power r k minus 1 log r minus 1. There exists some point in this interval such that for all constants less than this point, we have r-colorability with high probability. Okay, but this is the exact result. What can we say about the value of this point, urk? So they prove that urk can be chosen equal to this expression. So we have the same first term, summoned r to the power k minus 1 log r, minus this, and with some error term which tends to 0 with when r is large or vice versa, k is large, doesn't matter. So, but still, so we have the gap between this upper bound and this lower bound, and this gap has the order this, so r minus 1 over r minus 1 over 2 log r plus something bounded, in fact it will tends to 0. And when r is large, it is growing, so again we have log r over 2, the order of the gap. And the same question, can we reduce this length to a bounded value? So we can prove that there is an interval of a very small length in which we don't know the exact limit distribution. In the case when R is large, it was again proved by Kojoglon with cursors, Iyer and Greenhill, and they showed that if R is large in comparison with K, some greater some R0 of K.
What does 2015 plus mean? Does it mean 2017 plus?
I don't know, maybe it is not published yet, so.
But then it should be 17 plus.
I think it appeared in 2015, but still.
Huh?
This paper appeared in Arxiv in 2015, so.
On archive on the
Archive,
15.
yes. So I put here 2015 plus. So if C is less than this, so we have two first summands the same as it was in the upper bound. So R to the power k minus 1 log R minus log R over 2 minus log 2, again log 2, with some error term. And then with hypergraph, our hypergraph is uncovered. Okay, so and the main result of the talk states that we can do similar result, but maybe with some worse constant, but for every R and K. So in both regimes, when K is large in comparison with R, or R is large in comparison with K. So this is a statement. If R is at least 2, K is at least 4, and one of them is large, going to 0 is some absolute constant, and constant C is less than this expression, so we have again these two summands as in the upper bound, and R minus 1 over R, a bounded third summand, and the error term, which tends to 0, is gross of K over gross of R, doesn't matter. So then, with hypergraph, our hypergraph is uncovered. So this constant, when R is large and K is small, this constant roughly is minus 1, so which is our bound is less than this minus log 2. Log 2 is less than 1, so here it is. But it works when in the opposite regime when K is large and R is small, so R can be equal to 2, for example. But for 2, this result had been already known for a very long time. So we reduce the length of this ambiguity interval to a bounded value for any pair R and K. Okay.
So what were the conditions in the earlier result?
So it's
Go back one turns back.
sorry.
What are the conditions in the other corresponding result?
Corresponding. So here,
That's it.
Kojoglon, so the R is large in comparison with K. So they assume that K is some constant and R is very large. So they put a better result. Okay, so now some words about the second moment method. This method was used in all the previous papers, and so here I don't obtain any new technique, but in fact my approach seems to be very flexible and very much simpler than in all the previous papers. So what is the idea? How can we prove the previous theorem? So the first step is to consider another model of a random hypergraph. Instead of binomial model, it is better to consider, more convenient to consider uniform model, but not classical uniform model. Model of a random hypergraph with linear number of edges, so we have Cn random independent edges, so every edge will be chosen independent. And moreover, in every edge, we choose k vertices also randomly independently. So that means that our hypergraph, this random hypergraph, can contain duplicate edges, so probably some edges will coincide. And moreover, non-proper edges. Non-proper means that some vertices in an edge can coincide, In fact, it is bad because if you have a loop, all the vertices are the same, so you will not be able to color in any number of colors, so the chromatic number will be infinite. So you will always have a monochromatic edge. But for hypergraphs, this happens with probability tending to 0, so it doesn't matter in this case. And it is not difficult to prove that if our hypergraph is r-colorable, then for this constant c, with high probability, then for any constant smaller than c, in the binomial model we also have r-colorability with high probability. So c prime is less than c, but any is c prime, so it doesn't matter because we can assume that we make some restriction, some -1 here in error term. Smaller, okay. The second step is to use the fact that the r-colorability property has a sharp threshold. That means that there exists some function m hat such that for every positive epsilon, our hypergraph is r-colorable with, here should be 0. So here should be 0, not 1. With probability 1, if m is less than this m hat times 1 minus epsilon. So if you have small constant times smaller number of edges, then you have r-colorability, and vice versa. If you have a greater number of edges, then with probability, asymptotic probability 0, you will have r-colorability of your hypergraph. This helps in the following way. So it is sufficient to show that this probability that the hyperchromatic numbers at most r is bounded from 0. Okay, so then if it is bounded from 0, but maybe it doesn't tend to infinity, but if it is bounded from 0, that for any smaller constant it should tend to 1, because we know in this case that we have already passed the threshold, our threshold. And the third step is to consider balanced colorings. So what is a balanced coloring? So a balanced coloring means that all the color classes have the same cardinality. So if you have n vertices and r colors, then every color class should have a cardinality n over r. And the position that it is sufficient to prove the theorem when n is divisible by r. Because in the sparse case we have a lot of isolated vertices, so in fact it doesn't matter if we remove 1 or 2 of them, so the chromatic number will be the same. Okay. And now this is the main random variable, so let xn denote the number of proper balanced colorings over our random hypergraph in this uniform model with r colors. So the proper coloring with sizes of color classes equal to n over r. So if it is positive, then you know that it exists a proper coloring, so the chromatic number is at most r, and the public segment equality implies that this probability that xn is greater than 0 is at least the relation between the square of the first moment and the first moment squared over the second moment. So it remains to do the following. So we want to prove that the second moment is at most some maybe big constant depending on k and r are fixed now, times the first moment squared. So this is an idea. So all we have to do is to prove this, then this probability will be bounded from 0, and the sharp threshold will tell us that for any smaller constant we have the probability tending to 1. Then you should make some calculations, so this is straightforward to check that the expectation of xn has this order, The second moment can be calculated as in the following way. So what is the second moment? So we want to compute the number of pairs of balanced colorings which are both proper for our hypergraph. Which means that, okay, if we have two fixed colorings, then we consider the following parameterization, because we have a matrix A consisting of elements Aij, where Aij is a number of vertices such that the first coloring have the number of vertices in the color with the color I in the first coloring, and these vertices should have color J in the second coloring. So this is some kind of, so we have, and vertices divided into R square parts. So this is calculations, so you consider this. So the problem is that, okay, we can make some other representation. So the square, the second moment has the following order. So we can make some expression which will have the same order as the first moment squared, and some other and the remaining factor. So it should, here should be n to the power r minus 1 over 2, and some expression which is the sum over matrices. So the problem is first. So here in exponent we have some functions depending on matrix, on our matrix A. So f of A and g of A. F of A is just an entropy function, and g of A is this. Okay, and the second moment will not work if there exists A such that g of A is greater than f of A, because here we will have an exponent greater than 0, and so it will be very large. So the second moment will be much larger than the square of the first moment. So we want to prove that for any constant c less than something, g of A is always not is at most f of A. They are both equal to 0 if we have the matrix with all equal entries, so which means that every Aij is equal to n over r squared. It is easy to see that here the logarithm will be equal to 1, so this is some 0, and here this expression also will be equal to 0. And the key lemma, which gives almost everything, is the following. So under the condition of the theorem, there exists some positive functions that such that f of A minus g of A is at least this function, positive function b, times this, roughly speaking, this is just a square A of j normalized matrix. So we divide every element by n and then subtract the mean, so 1 over r squared. Then everything goes very easy, because if we have this, then we can substitute it here, and then for every value Aij, this expression has the order at most 1 over root n. So here in the matrix, so you recall that our matrix appeared from balanced colorings, which means that the sum over every row and every column is the same, which is equal to n over r. And roughly speaking, in the matrix we have only r minus 1 squared parameters, because if we fix, for example, in a row r minus 1 elements, then the last one will be exactly n over r minus sum of them. So the number of parameters is r minus 1 squared. So we have a lot of free parameters, which allows to use them, applying this relation to pairs. For example, Ij with such that the maximum of Ij is r, so the last column and the last row. and this will remove this growing factor n over r minus 1. Okay. The next step is, okay, if so this is the same. So I have already said that the number of free parameters in the matrix is r minus 1 squared, and the last sum, the remaining sum here after the substitution, can be approximated by a product of integrals, such integrals, but every such integral is some bounded value, is bounded, so we will have some bounded product. And this implies the required relation that the second moment is at most first moment squared with some constant depending on r. So, yes, we have some time also. Some remarks. Okay, the proof of the key lemma is simpler when k is large. When r is large, it is a little bit harder, but everything is simple because you don't need anything except some simple calculus, for example, Taylor expansion for a logarithmic function, so it's very easy. The condition of the parameter c is used only once in the very special case. So when the matrix, our matrix A, so A over M, so we can consider normalized matrix, it has a very special time form. So we have 1 over R minus something smaller. In fact, it should be something like this. And all the other entries will be so this is the first row, and all the others will be similar, but we should have this number on the diagonal. And so on, so we have this diagonal elements is roughly 1 over r minus something very small. And all the other entries are very small. So, which means that the colorings are almost the same. So the color classes are almost common size. So we have in a lot of vertices in one color. If we have some vertex set of the first color in the first coloring, then the first color class of the second coloring is almost the same. It's almost the same. So this is the most bad matrix, which doesn't allow to prove that the lower bound coincides with the upper bound. And this approach seems to be very flexible and can be used in the same way for other colorings, because, okay, so this function f of a, for example, it will be the same if we consider any other coloring, because it's just an entropy function which depends on the structure of the coloring, not on the structure of the type of coloring which we want to prove.
Like what?
Okay, I will give some example. Okay, I will give some example. For example, we can consider the following type of colorings, which, for example, has 3 colors. So 3 colorful. So hypergraph is said to be 3 colorful if there exists a 3 coloring of the vertex set such that every edge meets, for example, every of 3 colors. Or if here we have 2, that will be just usual 2 coloring, so property B. Okay, so this is 3 colors, so we want every color in every edge, but the number of colors is 3. And the same question, what is the probability threshold for this property in a random hypergraph? And together with 2 of my students, Nikolai Krofman and Dmitry Kravtsov, we were able to prove the following. So it's a sparse regime, of course, because this threshold will be less than the 2-colorability threshold, because this property is stronger. If C is greater than this, so 1 over 3 times 3 over 2 to the power k log 3 minus 1 over 2 log 3 with some error term, then our hypergraph is not 3-colorful with hypergraph, and almost the lower bound is almost the same, because here we have the same. The first 2 summands are the same, and their term is not the same. then our hypergraph is recolorable with hypergraph. So surprisingly, we were able to establish this threshold up to some exponential function of k. So their terms are both exponential functions of k. In comparison with the classical problem, here we don't have even a bounded. So we have a gap which tends to 0 with growth of k. Okay, so probably I will stop here. Thank you for your attention.
Questions? Comments?
In your method, you are using balanced coloring, but can they be used by lots and lots of people, including...
Yes, it's almost the same.
Completely
I said that I
Yeah.
use the same approach. In fact, it is absolutely the same as it was in the paper of Fries, Greenhill, and Dyer. I don't know why they were not able to obtain this result previously.
But your key lemma is lovely. It's very, very nice.
Yeah, yes,
it's wonderful.
Yeah. When I realized that, okay, their approach was the following. So let us try to find the minimum, but they don't consider in this equation. So the minimum of the exponent.
Yeah,
in
they
this,
need very heavy.
and then
they need heavy weather of it.
yes, and then you should compute the number of matrices and so on. But this helps you to deal with matrices very simple.
But do you know what could there be a nice form when you go back to your key lemma?
Okay.
Could there be a nice form of BKR?
Yes. So we can give some exact implicit
No,
expression.
but could there be the best BKR is a very nice function? It's a lovely inequality.
It's a nice function. So I don't know. We just obtained some rough bounds. So because our aim was to obtain any bound.
I'm sure you got somewhere, but,
Yes.
but there couldn't there be a very, very neat function there?
Very nice. Yes, I think so. Yes, it can be
It
nice.
would be worth having. It would be nice.
Yes. Yes. In fact, when k is large, it can be very nice. I think maybe r squared over 2 or something like this. It will be very nice when k is large. When r is large, it will not be very nice.
Paley and Zygmunt shouldn't be insulted with a lemma. Come on, I mean I'm sure that they would be very upset if that's their lemma. I mean, it's a triviality. I mean, like people wrote it. The next case is trivial, and it was proved by Hardy and Littlewood. And Littlewood found it very, very strange.
Any more questions? Okay, let us thank Dmitry.